Hi everybody, have a good time. This article is about using molybdenum disulfide and boron nitride nanoparticles for manufacturing self-lubrication nanocomposite by powder metallurgy by Mohammed J.F, ALOBAIDI and Ibrahim İNANÇ. Outlines for these articles start from goals, project plan, and experimental procedures and sample preparation. After sample preparation, we start for a characterization of powders and centered samples, and the results and the end. The goals start from first point, manufacture advanced engine without lubrication. Number two, study the adhesive wear behavior of the new nanocomposite under dry sliding. Number three, study the topography of worn surfaces of nanocomposites by using optical and scanning electron microscopy. Number four, use less expensive materials and more effective to produce the engine parts. Last one, the using of boron with nanocomposites instead of graphite, the effect of white lubricant. Here the project plan. Start from the left side. Left side from powder of microaluminum and powder of microsilicon. Make a blending by ball milling, that's mean mixing, and characterized by SEM and EVS XRD, and pressing, centering, and hardness test, and wear refraction test, and after that SEM and EVS for characterization for worn surface. Same process, but when adding 4 weight% of molybdenum disulfide or 4 weight% of boron nitride or 4 weight% molybdenum plus boron nitride as nanoparticles, that mean nano plus micro. Also same process by ball milling and SEM, EVS, and XRD for characterization, pressing, centering, and hardness test, and wear refraction, and SEM, EVS. Experimental procedures start from aluminum alloy, start aluminum powder plus 12 weight% of silicon powder plus molybdenum disulfide and boron nitride nanoparticles. Here is only base of aluminum. I will take one sample and take one sample of molybdenum plus this alloy and boron nitride plus this alloy, and take molybdenum disulfide plus boron nitride as hybrid addition to base alloy. Hybrid nanocomposites were prepared in 3 steps, which include mixing or blending the aluminum plus silicon powder with nanopowder via mechanical alloying method. And second stage is compaction or pressing and centering. We make X-ray diffraction analysis and hardness test and wear test under dry sliding condition, and investigation for microstructure tests by microscope, and SEM-EVS of selected samples are also made. The procedure of powder metallurgy starts from blending of the powder and pressing by compaction by press and centering. What we have aluminum silicon, aluminum plus silicon, this purity for aluminum and this purity for silicon was uh, the range of scale of size of in micro size for aluminum and silicon, plus nano size for molybdenum disulfide and boron nitride in nano size. Here we prepare 4 types of 4 alloys. Start from base alloy, aluminum silicon only with 0% of boron and molybdenum. Second alloy starts 4 weight% added to base alloy. That means 2 plus 2, 2 weight% of molybdenum disulfide and 2 weight% of boron nitride as nanoparticles. Second one is 96 of base alloy and 48% only for molybdenum disulfide. The fourth one is only 48% of boron nitride as nanoparticles. Now, what we characterize by XRD for aluminum plus silicon powder. What characterization after blending with nanoparticles didn't appear in nanoparticles but appear only for micro, but we characterize by SEM and EDS to characterize what's the new alloy. Here we can see the aluminum plus 12 weight% of silicon powder from this SEM and hexagonal boron nitride by SEM and molybdenum disulfide. The aluminum silicon powder by EDX, we see the peak of aluminum and silicon and EDS for SEM image. Here what happened for hexagonal boron nitride nanopowder and molybdenum disulfide nanopowder EDX. We prepare this mold as this shape, cylindrical and cubic shape, but in the standard we use cylindrical shape in all samples. Centering process. We use the centering process for 99.99 purity of argon and reach to 550 centigrade for 90 minutes and stay for cooling grade for 90 minutes also to room temperature with 2 liters per minute supplying of gas. That means we prepare 4 samples for base plus molybdenum disulfide for 48% and base plus 48% of molybdenum and base plus 48% boron nitride. Inspection for hardness was as below. You can see the improvement in hardness by molybdenum disulfide reached to 130 and 140 for boron nitride, but moderate percent for 48% molybdenum disulfide plus boron nitride was 124. Here the characterization of wear test. The wear test we see the base alloy was, as we can see from paragraph 48% as hybrid addition of molybdenum disulfide plus boron nitride based than all alloys. Another one here is 48% of molybdenum disulfide is also as good for decreasing the wear test. A study of worn surface by SEM, you can see by aluminum silicon alloy, it was as some difference from the crack from the base alloy. You can see from the what we addition 48% of molybdenum disulfide plus molybdenum is based than aluminum silicon base alloy and have high hardness and moderate wear test and increasing in wear resistance. We can see here the EDS for base alloy plus 28% and plus 28% of boron nitride. The base alloy plus molybdenum disulfide plus boron nitride. Here EDS for aluminum base alloy plus 48% only for molybdenum disulfide. And you can take conclusion for 6 steps. What happened? The improvement for aluminum silicon. The preparing the aluminum silicon alloy by powder metallurgy process give to us a good result, and it let us to prevent the drawbacks of custom manufacturing procedures. That's the benefit of use the powder metallurgy process. Second, the good characterization results were taken by SEM and EDS for the base alloy and hybrid nano addition. Third, the wear rate of the base alloy and nanocomposite samples increases with the increase of sliding time. But the hybrid nanocomposites show lower wear rate than the base alloy under the same load and sliding time. Fourth, the self-lubrication of aluminum silicon nanocomposite enforced by 4% molybdenum disulfide plus boron nitride has shown the base wear resistance under dry wear test condition. Fifth, the good lubrication properties of 4% hexagonal boron nitride than 4% of molybdenum disulfide. The incorporation of nanoparticles, molybdenum disulfide plus hexagonal boron nitride has hybrid addition in aluminum silicon result multifunctional application that require high performance. A suggestion for future work: number one, use different types of nano addition to the base alloy of aluminum silicon, like boron nitride and titania as nanotubes. Number two, spark plasma centering process. We can use it for limiting the drawbacks of the new structures. Number three, applying this project as a patent and participate with manufacturing teams to include this new alloy to project to produce a moving or carrier parts. Here is some references, and thank you for your attention.